In this web talk, I show how to use Mplus to do multi-step mixture modeling for latent class analysis. This is joint work with Tiamer Asparuhov and Linda Mutén. Multi-step mixture modeling concerns techniques commonly referred to as 3-step, BCH, and 2-step. The presentation illustrates several new Mplus features for these techniques that are included in version 9 of Mplus. Further web talks expand on the multi-step topic. Webtalk 9 presents new methods for handling measurement non-invariance represented by direct effects, and Webtalk 10 discusses latent transition analysis, which uses more than one latent class variable in contrast to latent class analysis. Together, these three web talks give a more accessible and comprehensive presentation of topics covered in Mplus Web Notes 15 and 21. Webtalk 8 is geared towards a non-technical audience and focuses on analysis ideas rather than formulas. It highlights Mplus syntax and Mplus output features. Statistical matters are discussed in a separate section at the end of the talk. Analysis illustrations use both simulated and real datasets that are available for practice. All Mplus runs are included on the website of the talk. Turning to slide 2, here's the outline for the talk. First, we give some background for why one would be interested in doing multi-step mixture modeling. And then I turn to the key aspect of measurement model analysis, which in this case is the latent class model itself, which is a first basic step in the multi-step analysis. Then I turn to automatic and manual multi-step approaches. First, we talk about the automatic approaches that we have in Mplus and that we have expanded a bit in version 9. We talk about automatic multi-step approaches for adding distal outcomes to the basic latent class analysis measurement model and adding covariates. So that's useful in some cases, but in most cases you will have to turn to what we call a manual multi-step approach that you set up yourself. And in that area we also divide it up into distal outcomes and covariates. So for the distal outcomes, we're going to talk about the familiar 3-step, BCH, and 2-step approaches, where 3-step is also sometimes called 3-step maximum likelihood, and BCH is sometimes called 3-step BCH. And this talk is going to spend some time on discussing the case where you have covariates that have missing data, a complicating feature. We're going to present several different approaches to that, to handling that by maximum likelihood and integration, using Bayes and using multiple imputations, and a combination of imputation and final model analysis. We're going to focus on 3-step here in the first 3, and in the last combined approach we take care of all 3. And then we're going to compare results using these different manual approaches. Turning to slide 3, we will then have a real data example using antisocial behavior measures that I have discussed before in previous short courses and articles. And that then illustrates some of the methods we talked about, but on this real data set. Then I turn to further topics, some specialized topics like class varying regression of the distal outcomes Y on the covariates X, and some considerations regarding last step analysis having to do with the starts option. And then I talk about CPROBABILITIES, class probabilities in the context of multiple imputation, before turning to the statistical methodology part, where we discuss in detail the issues of posterior probabilities and most likely class, which is essential for 3-step and BCH, And I'm talking about missing data on a binary covariate, and why class varying regression is an interaction. And then I talk about various kinds of Monte Carlo studies that have been done in the literature for the three methods. And then I end with an appendix where I discuss how I generated the missing data on covariates for the simulated data sets. Turning to slide 4, I want to give a background for multi-step modeling and introduce the concepts of the measurement model versus the full model. So top left here we have 6 latent class indicators of a latent class variable C, and that is our measurement instrument, those 6 indicators. In our analysis here, with simulated data, they're going to be binary. And the full model is the model that we're really interested in ultimately, and it adds to those 6 indicators a further variable, it could be several variables, in this case designated by y. So y is considered a distal outcome. It's a variable that's predicted by the latent class variable. In the measurement model analysis, you determine the latent classes, you determine how many they are, and you interpret them. One example is latent class analysis. There could be other measurement models as well. In the full model, you add other variables to the measurement model, and we have then the example on the right here of distal outcome predicted by the latent class variable. Now you may want to ask yourself, that distal outcome looks like just another indicator of latent class variable C, in addition to the 6 that we have here. And that is the problem, because we really want to consider these 6 variables as our measurement instrument that captures what C is, and then we want to predict Y from that C. And to be able to do that, we need multi-step modeling. So on slide 5 then, I give the multi-step rationale, claiming that there is a need to separate the estimation of the measurement model from the full model so the latent classes don't change from one step to the other, from the measurement model to the full model. Because that, for instance, that distal outcome in the full model may change the latent class formation. And that would be undesirable. For instance, if the full model outcome is measured, the distal outcome is measured at a later time point than the variables of the measurement model. Take, for instance, measures of aggressive disruptive behavior in the classroom in elementary school, and the distal outcome that is juvenile delinquency later on in life, and where you want to predict from the measures that you have in elementary school, you don't yet have the distal outcome Y, and you want to see how well you can predict from the early time point to a later time point. Covariates in the full model may also affect the latent class formation and the determination of the number of classes, and it's inconvenient to have them influence the latent classes. When you want to experiment with different sets of covariates, you would have to do the latent class enumeration over again. So the separation of these 2 estimation steps is done by the multi-step approaches that I'm going to present. So the first step, again, is the latent classes being determined only by the measurement model, and the last step, adding the distal outcomes and or covariates of the full model. And how we do that exactly statistically is shown in the statistical methodology section, and what I will try to do is to show it to you in a more intuitive fashion with as few technicalities as possible. So slide 6 then, we talk about the multi-step approaches of 3-step BCH and 2-step in a first intuitive fashion. Now, the 3-step and the BCH approaches use the so-called posterior probabilities from the estimated measurement model to determine each individual's most likely class membership and take its measurement area into account. And in the next couple of slides, I'm going to show you what a posterior probability actually is. So in 3-step, that measurement error is handled by the last step fixing logits of the measurement model. So those are the logits in the relationship between the latent class indicators regressed on the latent class variable. And that's done by taking measurement error into account in the most likely class classification that I will describe in a couple of slides forward. In the BCH approach, the last step instead uses weights from the measurement model to take measurement error into account in this most likely class classification. 2-step, the third approach, takes a totally different tack. It uses fixed measurement model parameters in the last step, fixing the measurement model from the first step and thereby avoiding measurement error and keep the classes the same between the 2 steps. Slide 7, then we take a closer look at what a posterior probability is and how it relates to most likely class, or MLC. So a posterior probability is a probability of an individual being in each class based on the estimated model and the individual's data. So the estimated model uses all individuals' data. And now we go and ask, what's the posterior probability for an individual? And that depends not only on the estimated model, but this individual's data. And in Mplus, these posterior probabilities for each individual and each class are saved together with the most likely class, MLC, using the CPROBABILITIES option of the save data command. So for instance, this is an example that we're going to see several times. 6 individuals, 3 latent classes. So you have the individuals here, individual 1 through 6, as rows, and the columns are probability of being class 1, probability of being class 2, probability of being in class 3, and with most likely class designation. So for instance, for the first individual, the probability that he or she is in class 1 is 0.5, and 0.3 versus 0.2 in the next 2 classes. So the most likely class is class number 1, which is the highest one. For individual 2, you have a very high probability of being in class 3, and the class probabilities for the other classes are lower. Here MLC is 3, and so on. So for each of these rows, the probabilities sum to 1, 0.5 plus 0.3 plus 0.2 is 1. And for each column, the average C probability gives the class probability. So you average over these values and you get 0.30. On slide 8, let's take a closer look at the measurement error in this MLC, most likely class variable. And I claim here that from the table of posterior probabilities for all individuals, it is possible to compute a summary table of classification quality. We're going to show this summary table for the example of the 6 individuals on the previous slide, but in real data you will get it for your whole sample, of course, for the whole sample of people in your data. Now, what we're looking at here is a table where the rows correspond to the latent classes of the latent class variable C, and the corresponding columns for the observed most likely class variable. So both of these variables are nominal variables, that is, unordered categorical variables. But here, C, representing the rows, correspond to the true status of a person, and the columns correspond to the observed counterpart, which may be measured with error. So let's take a look at an individual whose true class membership is 1. The probability then for the most likely class variable being observed as 1 is 0.56. It is not 1.0 as we would want it to be. It's not perfect correspondence between the two variables. We have measurement error in the sense that you could be misclassified as a category 2 person by 0.38 probability, and it's a category 3 person by probability 0.06. So just repeating then that MLC is a perfect measure of C if all diagonal elements are 1 and all off-diagonal elements 0, and non-zero off-diagonal elements correspond to MLC measurement error. Now the 3-step and BCH multi-step approaches take this measurement error into account in their last step analysis. And we actually work through this example of the hypothetical 6 individuals in the statistical methodology section in detail. It's not complicated, it's just cumbersome. What you will see in the Mplus output is this table here, which comes out as in the middle of a sequence of 3 tables, which we'll refer to as we get into a data analysis. Now, in Mplus, we have both automatic and manual multi-step approaches. And the automatic multi-step approaches are only available for certain settings, which simplify the analysis. But in general, you typically need manual approaches that have much more general scope. So you have the automatic column, the manual column, distal outcomes versus covariates. So for distal outcomes, we have the 3-step and BCH methods, whereas the manual approach can add 2-step. For covariates, we have only 3-step. It's called R 3-step, regression 3-step, regressing on X's, whereas the manual approach then adds BCH and 2-step. So following then, I'm going to discuss these two possibilities of automatic and manual, and begin with the common starting point of the measurement model, the first step of the analysis. Turning to slide 10, the outline shows that we are ready to talk about the measurement model analysis. So on slide 11, we have a measurement model that is a latent class analysis model. We have 6 indicators, 6 latent class indicators of the latent class variable C. In this talk, we're going to mostly focus on binary latent class indicators, where the influence from C to U is captured by class varying probabilities of U equals 1 versus U equals 0. That's parameterized in Mplus via thresholds. So a high threshold gives a low probability for U equals 1. We can also have ordinal variables where the influence of C onto U1, for instance, is captured by more than 1 threshold. So if you have 3 categories, you will have 2 thresholds. You can also have unordered variables, nominal variables, where the influence from C to U would be represented by means on the logit scale for that nominal variable. Or you can have continuous latent class indicators, where the influence from C is captured by class varying means of the continuous indicator. Or you can have count indicators, where the influence is captured by class varying means of the log rate for the count model. And you can mix all of those different possibilities in the set of latent class indicators. Now, class enumeration, deciding on the number of classes, is determined as part of this analysis of the measurement model. And for a more full discussion of LCAs, you can look at our short course videos, topic 5. So if something seems unfamiliar to you as I go through slides in the future here, just go back to short course topic 5 and refresh your memory on those topics. Slide 12 then shows a first input for Mplus, and the data file is called distal.dat. It is a simulated data set that I created, and it's used for several different analyses in this Webtalk. The sample size is 1000. And here is the list of the variables in the data set. And the variables that we're going to use for the analysis, the use variable, are U1 through U6, the latent class indicators. Missing data is flagged as 999, and we declare the indicators as categorical, meaning that they can be binary or ordinal as determined by the program. We're going to ask for 3 classes in our analysis. And we do a mixture type of analysis, which implies that we have the possibility of multiple maxima, and we want to choose many different random starting values, which are perturbations of the default starting values. So we have an initial set of starting values that are used for initial iterations, and then Mplus picks the 10 best of those for a full iteration to a solution. I use processors equal 8 or 12 on my computer, and you can see what choice is best for you on your computer in terms of speed of analysis. But using several processors is important when you have mixture modeling with many starts. And then I ask for technical output, the parameters that are free and fixed, etc. And Tech10 giving univariate and bivariate frequency table fits. And note here that no model command is needed, because we have the default of the thresholds or the probabilities of these binary items in this case varying across all classes by default. So that's the whole input for the measurement model. On slide 13, you have the output of Mplus showing the results of these random starts ranked from best to the worst log likelihood values. So you have 10 of these here corresponding to the last 10 full iterations that we make. And you see that they're all the same. And here the likelihood is on the negative part, so a good likelihood is the likelihood that's as close as possible to 0. The unperturbed is rather the default starting values, and in this case actually we wouldn't have needed any random starts at all beyond that. But that's because the model is fairly well behaved, as it often is in simulated data. Slide 14 then gives you excerpts of the model fit information, 20 free parameters in this case, the log likelihood value for the model, we call it the H0 model, and the BIC value, the Bayesian information criterion, which we want a low value for. And we compare it then to having, say, 2 classes instead of the 3 we used, or 4 classes instead of the 3 we used. And at the bottom then you get the final class counts based on the estimated model for each of the classes, the number of people, and the proportions, so the class estimates of the class probabilities. In this case, the entropy is 0.68, so a moderately high value. Slide 15 then shows important output, 3 tables that come out in the Mplus output. The top table is not that informative. It's really an intermediate step to get to the second or middle table. And we discussed the transition from this table, the top table, to the middle table in the statistical methodology section. So that for now we're focusing on the middle table. And we looked at that before on slide 8 for the hypothetical data for 6 individuals. Here you have it for these real data individuals. And so the rows here represent the true latent class status, and the columns represent the most likely class being 1, most likely class being 2 or 3. So for instance, for people who are truly members of class 1, they have a probability of 0.864 to get a designation of most likely class of 1, that is the correct designation. But they also have a chance, lower probabilities, for being misclassified into most likely class 2, most likely class 3, whereas the true status was 1. So you have true status, true latent class variable, and then the observed fallible measurement error prone indicator of most likely class. Now the bottom table we're going to discuss later, the logits here, which will be used for 3-step analysis, one of the 3 multi-step procedures. On slide 16 there we have a table that I presented in a way that I like to use to interpret my solution. So you have a 3-class solution here, 3 classes, and you have the 6 latent class indicators. And here in the table are the probabilities for u equals 1 as opposed to u equals 0. So for class 1, you see then that you have high probabilities for all 6 latent class indicators. Class 2, you're high only on the last 3, low on the first 3. And for class 3, you're low on all 6. So let's take a closer look at how these indicators define these 3 classes. It's good to understand that, for instance, in terms of measurement instrument development. So I'm claiming here that U1 through U3 are key for defining class 1, because they're the only indicators with high probability for only class 1. You know, these variables, these indicators, have high probabilities only in class 1, not in class 2 or 3. Whereas U4 through U6, they're high also in class 2. So the first 3 are key for defining class 1. U4 through U6, the last 3, they're key for defining class 3, is what I claim. Not class 2, but class 3. What do I mean by that? Well, those last 3 indicators are the only ones differentiating between class 2 and class 3. So the first 3 items, they don't differentiate between class 2 and class 3. They have low probabilities for both classes. But the last 3 items, last 3 indicators, are high only for class 2 and low for class 3. So they are key for defining class 3. You can want to think about that. Now all of these 6 indicators are needed to define class 2, where the first ones are low and the last ones are high. That's the only class that has that feature, and you need all 6 to define it. Now you can look at that in more detail. The second sub-bullet here, the p-value sub-bullet, which shows up on the next slide, where the small p-values on the next slide for class 1, that's testing the difference in probabilities across classes, where you have small p-values, significant difference, class 1 versus the other 2, so class 1 versus the other 2. And likewise, to define class 3, you have small p-values for class 3 versus the other 2. So this is a little bit more involved. Slide 17 is actually a new feature in version 9. So it has to do with latent class indicator discrimination between classes. How well does an indicator discriminate between classes? You want to know that. So we do a quality test of probabilities across the latent classes. So here on the left, you have the first 3 indicators. On the right, you have the last 3 indicators. And here then, you see the low p-value 0 here for class 1 compared to the other two classes. There's 0. Same thing for U2. Class 1 versus 2, class 1 versus 3, both of those 0. Whereas for U4 through U6, it's actually class 3 versus the other two classes, 1 versus 3, 2 versus 3. They are 0 here, showing that they're the ones that discriminate class 3 from the other two. Just like we said here, U4 through U6, key for defining class 3. So those are two slides that can benefit from thinking through how this works out. So classes that indicated discriminate well between have low p-values, and discriminate poorly between give high p-values. Turning to slide 18, we're going to take a look at the automatic multi-step approaches, covering both distal outcomes and covariates. So on slide 19, the auxiliary option is introduced. So it's automatic, which means that you can do a single run to analyze the measurement model while also adding the full model variables using this auxiliary option. And you have distal outcome settings and covariate settings for this. So the distal outcome settings are variations of 3-step that I mentioned on slides 6 and 9 earlier, and variations on BCH. For covariate settings, we only have a 3-step variation called R3-step. There are many other settings for the auxiliary options that we have worked with in the past and investigated in the past and discussed in WebNote 21, but they're no longer recommended by us. On slide 20 then, we're focusing on the automatic approach for distal outcomes. And here is the list of the different distal outcomes, the acronyms for those. And we're going to take a look at them in more detail further on. So let's focus on the pros and the cons of this automatic approach vis-a-vis the manual approach. So the pros of this is the convenience of doing a single run, and no need to save class probabilities and fix low digits from the first to the last step, which we do in 3-step analysis, or save the BCH weights that we use in the BCH approach. So that's the convenience. And the limitation is that the distal outcomes cannot also be regressed on covariates, which you may want to do in many cases. So for that you need the the manual approach. And with several distal outcomes, the analysis is not done jointly for all of the outcomes, but one variable, one distal outcome at a time. So missing data methodology does not come into play. And that's an advantage of the manual approach once again. An exception to that is that type-X imputation analysis can be used. So data type equals imputation, which is described in the manual section where I talk about the imputation matters. And another disadvantage is that only one latent class variables can be handled. The LCA, of course, only deals with one latent class variable, so that's not a limitation in that case, but it would be in latent transition analysis, for instance. So slide 21 then talks about the automatic approach for covariates. So pros and cons of the auxiliary are 3-step. There's only one approach for that in Mplus. Pro, again, is convenience, single run, no need to save the C probabilities and fix the low digits. Limitation, observations with missing data on one or more of the covariates are deleted, just like in regression, with the exception of typicals imputation. Direct effects from covariates to latent class indicators, differential item functioning or measurement non-invariance cannot be included. And actually that's covered especially in Webtalk rather, Webtalk 9. And again, only one latent class variable can be handled. So let's take a look at the distal outcome version in an actual analysis here using automatic multistep. So let's take a look at slide 23, where the full model includes distal outcomes Y added to the LCA measurement model. So we have 3 distal outcomes here. Y1 is continuous, Y2 binary, and Y3 ordinal. So we're going to use the automatic approaches of auxiliary BCH and BCHC, where C stands for the categorical cases, which covers both the binary and the ordinal case. So here's the input for auxiliary BCH. It's the same data set, distal.dat, that we talked about before. And the use variables are still U1 through U6 here, except that we also add the auxiliary statement where we want to bring in the full model variables of Y1 through Y3. Y1 is continuous, so we use the BCH approach. Y2 and Y3 are categorical, binary and ordinal, so we add C to that. It's also possible, as I say here, to mix it up, to have BCH options mixed with 3-step options, and the different variations of that. Now, for this case, we still then have the typical mixture analysis specifications as before, but no model command needed here either, because the threshold probabilities vary across all classes by default. So this is all you have to say. So we do step 1 using the U1 through U6, and the full step, the final step, full model final step adds the 3 Y variables. And then Mplus provides tests for these distal outcomes. Y1 is continuous, so we test mean differences across the classes. First, we note that the number of observations deleted for this variable is 178. So Y1 has missing data, and the ones used are therefore 822. So we lose some people there. And this is what you can avoid when you do a joint analysis of all 3 Y variables using the manual approach. But often the drop is not that big. And the means then of the classes are listed here, the standard errors. And then we also provide a chi-square test of differences between these 3 means overall and for each class versus every other class. And p-values are significant here, so there are significant differences across classes in the Y1 outcome, distal outcome. For the binary Y2, we give several statistics. We give the probabilities in the different categories of the outcome and for the different classes. And we give the standard errors of those probabilities, but we also, more importantly, give the odds ratios. So an odds ratio, as we know, is a measure of a relationship between 2 variables. So what are the 2 variables? Well, it's the distal outcome with its 2 categories and the latent class variable. And we compare then each class to the last class. So each category here, it's the second category compared to the first, and the classes are compared to the last class. So the odds ratios be 1 for the last class here. So for instance then, if you look at class 1, you have the odds here of being in class 2 versus 1 as this 0.676 divided by 0.324 for class 1, and for class 3 it is 0.437 divided by 563, so much smaller ratio, much smaller odds rather. And if you take the ratio, the first to the last, you get this odds ratio 2.688. You may want to try that. And you also get a standard error for that, but more importantly, you want to work with these non-symmetric confidence intervals for odds ratios. So for instance, then for the category 2 of class of the binary outcome, you have a confidence interval that goes from 1.7 to 4.0. So it is not including the neutral point of 1, which means it's significant. So the odds rate, the Y2 is significant differences between class 1 and class 3. For the class 2 versus class 3, you have a confidence interval that includes 1, so this is insignificant. And we also give chi-square test of these differences overall with p-values, and we see that all differences are significant except class 2 versus class 3. And you can see that already in the probabilities here. The ratio of these probabilities are fairly similar and therefore cause the insignificance. So in conclusion, the answer to the question, does the latent class variable have an effect on Y2? Well, when we compare class 1 with class 3, the answer is yes, because the confidence interval does not include 1. But when we compare class 2 to class 3, the answer is no. We have an insignificance there. Confidence interval covers 1. And this is also seen in the chi-square test section at the bottom when we test differences in probabilities. We have an overall test, but we were looking at the class-specific test and we see the significance here, but not for class 2 versus class 3. Degrees of freedom is 1 for those class-specific comparisons. Turning then to slide 27, we look at the ordinal Y3. So here we have a 3-category distal outcome. So the question is, does the latent class variable have an effect on Y3? So let's take a look at the details here. So now we have 2 odds ratios per class. For example, for class 1, we can consider the odds both for category 2 versus 1 and category 3 versus 1. And we can compare those 2 odds with the odds that we get in class 3 and thereby get odds ratios 0.998 to 1.033. Now, if you look at the confidence intervals, you see that all of the odds ratios here include the confidence interval for the odds ratios include 1, and therefore there's nothing significant. So no effect of the latent class variable on Y3. And that's because of the population values that we used for the Monte Carlo simulation that generated the data. We see then that if you look at those in the appendix, you see that the population values differ much less for Y3 than for Y2. For Y2 we did find some significance, but here for Y3, for those differences, we don't have enough power to detect the differences even at the sample size of 1,000. The insignificant result is also seen in the chi-square testing at the bottom of this slide, where the p-values for the class comparisons are not small. So we can't reject that they are equal. And note here now that we have 2 degrees of freedom for the class differences. That's because we have 3 categories for Y3. We had only 1 degree of freedom for Y2 because it was binary, but now we have 3 categories for Y3, so that when you do testing of probabilities, you know, you get with 2 categories, you have 1 probability to test because the probabilities add to 1. With 3 categories, you have 2 degrees of freedom because those probabilities add to 1 as well. Turning then to covariates on slide 28 for the automatic approach. Slide 29 gives the model. We're going to work with 3 X variables and illustrate auxiliary or 3-step. So on slide 30, you have the same distal data set rather, and the use variables are still U1 through U6, corresponding to the measurement model of step 1. And the outcomes, or rather in this case the covariates, are x1, x2, x3, and we use the R3-step regression, 3-step, C on X regression approach. And we note here, for instance, a little detail: x1, x2, x3 are not consecutive names on the names list. The x1, x's, and the y's are mixed up here, so you better specify them without the list function. And you just note that this parenthetical R3-step can alternatively be placed after each variable. And again, no model command needed. So this is all you need to do for the auxiliary R3-step. Now, with R3-step, we have list-wise deletion applied to the auxiliary variables. And to avoid that, you can take the tack of data imputation, followed by analysis with type calls imputation, which I will illustrate in the manual approach section. The number of deleted observations again here is 332, and the ones used 668. So you lose quite a big chunk of data in this set, in this example, with the distal.dat data set. In most cases, or in many cases, you don't have that missing data on X, and it's not worth it to get into imputation matters. So here you have the results for auxiliary R3-step. So you have 3 classes. So you have C#1, class 1 on the 3-axis, and class 2 on the 3-axis. Whereas the coefficients, the loaded coefficients, are 0 for the last class. So we are comparing to the last class as usual in this multinomial logistic regression of C on X. So what we present in the output, this output section, is odds ratios. So these are odds ratios given here, estimates, and we focus on the 95% CI, the non-symmetric confidence interval, and look at the significance of that. So here it looks like X1 has a significant effect, and X2 does, and X3 as well. This is regarding class 1 versus 3. But for class 2 versus 3, you include 1 here. So that's insignificant, this is significant, and this is insignificant. Slide 33 once again shows the outline for the talk. And we have now come to the topic of manual multi-step approaches, which is the primary reason for creating this web talk. This is going to be the approach that you probably most often will use. So there are several advantages of the manual approaches compared to the automatic approaches. First of all, now we can have a regression of the distal outcomes onto covariates, which is often something we want to do. And observations with missing data on those covariates don't have to be deleted. We're going to show several ways of dealing with missing data on covariates. Furthermore, direct effects from the covariates to the latent class indicators, which indicate measurement non-invariance or differential item functioning, can be included. And that's going to be a topic for Webtalk 9. Also, with several distal outcomes, the analysis with respect to those outcomes is done jointly, so that missing data methodology is used. And also, more than one latent class variable can be handled, which is, of course, essential for latent transition analysis. But still, even for the manual approach, the first step is the analysis of the measurement model, and the last step now can be done by the three different methods of 3-step, which uses fixed logits from the measurement model to correct for measurement error, or BCH, which uses weights from the measurement model to correct for measurement error, or using 2-step, where the last step fixes measurement model parameters. So let's take a look at the case where we only have distal outcomes. So on slide 36, we show an example of a full model where the measurement model has been added to by 3 distal outcomes. And the distal outcomes here in this case, one variable y1 is continuous and has missing data, and the second is binary with missing data, and the third is ordinal with no missing data. So now we can think about doing a joint analysis of the 3 y's in the last step and apply missing data methodology. If you only had one distal outcome y1 with missing data, which we have here, missing data methodology, FIML, cannot help you. You need more than one outcome for that to come into operation. But here now with 3 of them, and with one that especially that does not have any missing data, the missing data methodology applies. So let's then take a look at 3-step, a manual 3-step, and the first step. So the first step is the same as the measurement model, as we say here, but we're adding save data of C probabilities down here, bolded. The data set is still the distal.dat data set with these variables in the columns of the data set. The variables that we're going to use are the, in the first step, are the 6 latent class indicators, which are categorical, in this case binary. And now we're going to use the auxiliary option once again. An auxiliary option refers to variables beyond those of the use variable option. In this case, we're only using the auxiliary option to save variables together with the C probabilities that we save at the end here. So we're not using it for automatic 3-step BCH as we did before, where we have parenthetical expressions with 3-step and BCH connected to these variables. So these 3 variables are the additional variables, the distal outcomes that we add to get to the full model in the last step of 3-step. So we save the C probabilities, which carry that file carries information, and that we will use in the last step. And we put them in a file that we call CPROBY here, since we're only dealing with distal outcome y's. And the save data information is given here. The save file name is cproby.dat, and then you get the variables, the use variables, plus these auxiliary variables that we had, plus the class probabilities for the 3 classes, and the most likely class designation for the latent class variable C. Most likely class for C. And we also, in that first run, get the third table that I've been talking about earlier from the Mplus output. You have the logits for the classification probabilities for most likely class membership by latent class row. So you have these logits here. We don't concern ourselves with the last category because it's fixed at 0. by default, but those 2 by 3 6 numbers should now be entered into the analysis in the last step. So here we have input for 3-step, last step. And now the data file that we work with is no longer the original data, but we work with CPROBY.dat from the first step. And that means that we have a new names list, which was shown then at the bottom of, or on slide 38. And we then replace the name for the most likely class for variable C by the simple letter N. N standing for a nominal variable, but it's the same as the MLCC. So the use variable list for our final step analysis is consists of the distal outcomes plus that nominal most likely class variable called N. And since we have categorical outcomes, 2 of the 3 Y's are categorical. We give that categorical list there, and we specify N as a nominal variable, 3 categories. And now the missing data is designated by a star instead of the 999 because it's a new data set. And that was shown on slide 38 as well, that missing data is now denoted asterisk or star. And since this is the last step analysis in the mixture modeling, we use starts equals 0. More on that later. And now we have a model statement for each of the 3 classes, C#1 to C#3. And we have the values that we looked at before, the loadits on the previous page down here. 2.706, 0.310 for instance, 2.706, 0.310. So we give the first 2 categories of the nominal variable N and their loadits, and they are fixed. So we have at here. And then we go down to the next row of loadits, minus 0.121, 2.499, and so on for the last class. So those are the values that we have to give for 3-step. Now the other variables on the use variable list, y1 through y3, their means for the continuous y or thresholds for the ordinal y2 and y3 vary across the classes by default. So they don't have to be mentioned. You could mention them within each latent class here, but they don't have to be mentioned. Now let's turn to the second multi-step method, BCH. So the first step once again goes back to the original data, distal.dat, with its names list. And since the first step, we're going to use only the latent class indicators. And now we're going to once again save the distal outcome variables for the last step. And in this case, we save them together with BCH weights, the weights that BCH needs for the last step. So that's instead of the fixed loadits. So the file is bch.dat. And we see the saved data here in bch.dat, the latent class indicators, plus the distal outcomes, and now plus these 3 BCH weights corresponding to the 3 classes. And again, the missing data symbol is an asterisk. Slide 43 then shows the last step of BCH. And the file name is now bch.dat, and it has its own names variable list that we just discussed. And the use variables are y1 through y3. That's the only variables in the model. You don't have the nominal indicator N, and the weights come into play in this option. Training equals weight 1 through weight 3. I just simplified the weight name from the page that we have here. Instead of BCH weight 1, Just call them weight 1 through weight 3. Parenthesis BCH. And again, starts equals 0. And again, no model is needed because the Y means and thresholds vary across the classes by default. We don't have any model here because we don't have any fixed n nominal variables in the BCH approach. Turning then finally to the two-step approach, what is that like? Well, first step is the same as the measurement model. So we go back to the original data, and we have the use variables U1 through U6 again, the latent class indicators, they're binary, and we have a moderate number of starts. And now the only thing we do here that's specific to two-step is ask for S values. You know, you save the estimated values thereby in a file, or you have them in the output rather, but it comes out in the output and you can just copy them there. This is what they look like, shown on slide 45. So in the output you find these values for class logits and for the latent class indicator logits for the three classes. So you can copy this. You don't need this part, the C# part. You can copy only the C1 to C3 information for the latent class indicators U, and you use then the Mplus editor to replace the asterisks with @ to make them fixed instead of free, and you do a global replacement where you want to make sure that no unwanted changes of asterisk occur, such as the missing data flag in missing equals asterisk, so that you may end up with that being an @ instead of an asterisk, so you have to change that back. Anyway, so these are the values you take for the last step on slide 46. And note then that for two-step, the data set is now the original data set. There's no special data set saved for two-step. All we saved it's the measurement parameters that we just looked at on the previous page, but now with @ instead of asterisk. So going back up, the use variables are U1 through U6, the latent class indicators, because they're mentioned here in the model here in the last step, and that's specific to two-step, that you have the latent class indicator variables in the last step. You don't have that in the three-step or BCH. And you have the three distal outcomes. And these are the categoricals. And you have starts equals 0. And once again, the Y means or thresholds vary across the classes by default. Now, on slide 47, I point out that in the automatic approach, we got some automatic results coming out, and that includes odds ratio results. The automatic approach produces odds ratios and their non-symmetric CIs for distal outcomes. They're binary and ordinal. But with the manual approach now in version 9, we have added these outputs in the in various sections in the output. So you have them for the manual approach as well. And they're under the heading latent class indicator odds ratios for the latent classes. So it's automatically computed. Now you can do it by hand, so to speak, by using models constraint. And I showed how to do that actually in Webtalk 2, slides 17 to 20 if you're interested in the detail. Slide 48, I point out that the automatic approach produces chi-square testing of intercept and threshold differences across the classes, testing if the classes actually have a significant influence. Using the manual approach, these are found under the heading equality test of means and probabilities across the latent classes. So that's kind of testing is also available with covariates when the regressions of the distal outcomes on the covariates are not class varying. So that's a way to see how the latent class variable influences, or test how the latent class variable influences the distal outcomes. On slide 49, we turn to the key topic of having not only distal outcomes, but also covariates with missing data, a very common situation that we'll take our time discussing in some detail with different approaches. Slide 50 shows the model that we're going to consider. We still have the 6 latent class indicators. We have the 3 distal outcome variables that we looked at a little bit earlier. And now we add 3 covariates X. Again, the latent class indicators are binary. The distal outcomes is a mix of continuous and categorical with missing data. And now what's new is the covariates, where X1 is binary, common feature, and X2 and X3 are continuous, and we have missing data on X1 and X2. And importantly here, the slopes in the regressions of Y on X are not class varying. And that's important for understanding the effect of C on Y. So effect of C on Y is seen in the class varying y-intercept and thresholds, but that's only the case when the regression slopes of y on x are not class varying. In the further topic section, we discuss class varying y on x, so class varying slopes as well, but that's not the case here now. Slide 51 takes a look at the Monte Carlo generated data. That's the distal.dat data set again, and where the sample size is 1000 and the entropy is 0.74, moderate entropy. And in the output, you will see that we have missing data on the covariance shown by the covariance coverage output. So for the 3 axes, we have the coverage, univariate coverage, and the bivariate coverage. So for instance, for X1, 81% of the sample is observed, which means that 19% is missing, and that's the same thing for X1 and X2. Now, in line with the regression analysis, individuals with missing on one or more of the covariates are deleted in the analysis with covariates when you don't take into account the missing data. And then the sample size drops from 1000 to 668, which is a 33% loss, pretty big loss. 0.668 is the same as this number here, where that's the case where X1 and X2 are both observed. Now, X1 and X3 has no missing data. Now, so this loss can be avoided, as we say here, by bringing the covariates into the model, that is, estimating their marginal distribution by covarying them using the with statement, or alternatively by using multiple imputation. Slide 52 then. I'm talking through various kinds of approaches, manual multi-step approaches, which deals properly with missing data on X in the last step analysis. So you can bring the covariates into the model, or you can do multiple imputation. When you choose to bring the covariates into the model, you can use maximum likelihood and numerical integration, or you can use Bayes. With ML, you have the choice of 3-step, whereas BCH is not available with numerical integration, and 2-step. So 3-step and 2-step are available, not BCH. And the advantage here with the ML numerical integration is that you get likelihood ratio testing available. The negative part is that you cannot handle many covariates with missing because of the numerical integration getting too heavy. And the approach can be somewhat unstable with large amounts of missing data and can be imprecise without adding many integration points. And finally, you cannot specify that you have categorical covariates like the binary X1. The base approach is also available for 3-step and 2-step, but not available for BCH, because base and weights don't go together. The advantage is that this is fairly stable analysis. It doesn't have the integration problems that ML has. And the negative aspect is that you don't get the likelihood ratio test, and computations can be slow, particularly with large samples. And that, again, you cannot specify categorical covariates. That's the same disadvantage as with ML. And finally, then, multiple imputation, where you have all three methods available. And the pro is that it's stable. You can specify categorical covariates, so X1 will be handled properly. And you can use non-model variables for missing data imputation. So you can bring in other variables with other information than what you have in the model variables. And the con is that you don't have the likelihood ratio tests easily available, and it can be slow with many covariates with missing. Now, the one method that is available for all of these three different approaches is 3-step. So we're going to demonstrate 3-step here only, but as an exercise you can try 2-step, for instance, or BCH when you do multiple imputation. So where are we in the outline? Well, we're in the manual multi-step approach. We are dealing with distal outcomes and covariates with missing data, and now we're going to take a look at a first approach here, ML and integration using 3-step. So slide 54 then looks at the distal.dat that we generated, the one replication Monte Carlo generated data that we are working with. That's a variable list. And we're going to use the latent class indicators. That's what we always do in the first step. And they are categorical binary. Missing data is designated that way, 3 classes. And what we want to do now is to save variables for the last step. Then this is the new feature then that we have X1, X2, X3 here in addition to the distal outcomes. Otherwise, this is the same as it was for distal. Apart from the fact that now we save a data set called CPROBYX to differentiate it from CPROBY that we had before. But since we're dealing with 3-step, we're saving CPROBs. So what we have here then is the save data. We save the U indicators, the X's and the Y's, and CPROB 1 through 3, and the most likely class. Slide 56. With 3-step, we need the logits. So these are the same logits as we had for the first step of slide 39, because it refers to the measurement model. First step is the same. Last step of 3-step with integration then, what do we have? Well, the data set we're working with is a CPROBYX.dat with the variables laid out this way, as we saw in the save data. And we're going to use X's and Y's, because they're the ones we're interested in, of the full model in the last step. But with 3-step, we also have the nominal variable, most likely class, that we call N here for simplicity. So that's declared as nominal. What's categorical? Well, Y1 and Y2 are. But we don't have the possibility of declaring X1 as categorical, despite the fact that it's binary, and that was a disadvantage of this method. 3 classes, estimator MLR, and starts equals 0 because we're in the last step. And now we have to specify algorithm equals integration. And we're going to have 2 dimensions of integration here due to missing data on x1 and x2. x3 doesn't have missing data. So you can see that when you have many x's with missing data, you're going to get many dimensions of integration. It's going to be very heavy computations. In this case, we have to use integration equals Monte Carlo. And as the comment says here, it's due to the partial missing x variables. So partial missing means that for some people, you don't have missing on x. So that's different from latent variables where every person has missing data. And that feature, the partial missingness, calls for Monte Carlo integration. The default is 500 points. With missing data on many axes, you may need more points. The input continues on slide 58, and where the key feature is that we covary the x's with each other here, and thereby bring them into the model. The disadvantage of that is that the binary x1 is treated as continuous normal. And we discussed that in detail in the statistical methodology section. It's not a big disadvantage, but it is an issue you should be aware of, and a problem or an issue that's avoided by multiple imputation. We have then the familiar fixing of the nominal most likely class variable at these different loaded values. So that's 3-step with integration. So then let's turn to the next manual approach, distal outcomes with covariates missing data, and we are on to base. So here we are for base. 3-step using base in the last step. No numerical integration needed. So the data set is still the CPROBABILITIES because we're still doing a 3-step, albeit in a base framework. So we have the names list here from that data set, and we're going to use x's and y's, but also this nominal most likely class variable. And the estimator now is base, and we ask for a certain number of base iterations. At least 5,000 is what we're saying here. Start is 0 still because it's last step. Now turning to the model here then, it's the same as for ML with the integration. We bring in the axis using a with statement, and we have fixed the nominal n variable, most likely class variable, at the loaded values that we had before for ML. For the ML approach. So the new feature here really is the estimator base, and with base we usually want to monitor Tech8 to see that the base iterations go well and go down to PSR values close to 1. And in version 9 of Mplus we've added another indicator of good convergence called effective sample size, and that is a useful feature, and I'm not going to talk about ESS right now. I'm going to only refer to a FAQ that we have or have on our website about that. That indicator or indication of convergence calls for close to 20,000 iterations for us to have a trustworthy solution, as opposed to the 5,000 that we start out with here. So you would have to rerun it with, say, 20,000. But that's okay. Slide 61 then, we turn to the third possibility, multiple imputation. And we're still going to stay with the 3-step approach. So multiple imputation it's generally not needed for missing data in the latent class indicators of the measurement model, or for missing data in the distal outcomes. the FIML approach is sufficient, using all available data. But multiple imputation is useful for missing data on covariates, because the imputation model can bring in variables related to missing data that are not in the model. So they bring variables that bring information that you don't have in the variables of the model. No numerical integration is required after the imputation, because there's no longer any missing data after imputation. And we have all three methods available to us. Here's a good paper, a technical report, multiple imputation in Mplus, and with some practical advice for avoiding problems in the imputation. 17 general tips from our experience with difficulties for certain situations. So what does 3-step with multiple imputation look like? So we're considering the imputation step with data from the first step of 3-step. So the data set is CPROBABILITIes from the first step, and with that names list. And the use variables that we have here are the x's and the y's. These are the variables used in the basic analysis down here at the bottom to provide sample statistics, and they're also the variables that are saved in addition to the variables on the auxiliary list, which is the nominal n that we need, the most likely class variable that we need in the last step. So now we do the data imputation step here, and we have a name statement and an impute statement, and this is new to version 9 of Mplus. The imputations use information from the variables on the data imputation names list. So these are the variables that contribute information to imputing, and impute, that option, concerns imputing values for variables on that list. So we're imputing x1 and x2, but we draw on information from the use and from the from x3 and from y1, y2, and y3. And in parentheses here, we state whether a variable is categorical or not, binary or ordinal, both in how we use it for imputation and how we impute. So we impute that as a binary variable in that case. The names list must include all use variables. And in this case, we request 100 imputations with a thinning of 100. So we don't record every iteration, we record every 100th iteration to avoid autocorrelation between the draws. And we save that as an impute star.dat data set, which gives you all 100. So analysis is type goes basic, sample statistics use for the use variable computed after multiple imputation done by Bayes. Here you can specify the number of Bayesian iterations referring to the data imputation step, and you can monitor by Tech 8. The computation that's done using type equals basic is done by WSMV, the WSMV estimator, after the imputation, computing the sample statistics for the use variables. On slide 64, I take a closer look at what's happening with the data imputation. In the Mplus output, you get specifications for the imputation. We see the number of imputed data sets that we asked for, and a default setting is activated, so-called H1 imputation. H1 referring to an unrestricted model in line with language of structural equation modeling, where you have H1 and H0. H0 can also be used for imputation, But here it's the unrestricted H1 model, and with the default covariance setting, which is described in the technical document for imputation that I mentioned. We use thinning with 100, and we have 12 dependent variables, 12 variables altogether, and 82 number of parameters. So what does this mean? Well, first of all, the number of variables and the H1 parameters are determined by data imputation names list. So the names list here, we have 6 U variables, 3 X variables, and 3 Y variables. So 12 all in all. And then you can figure out the number of H1 parameters. It's computed as follows. You look at the number of covariances or correlations. That is the off-diagonal element in a covariance matrix. 12 times 12 minus 1 divided by 2 is 66 parameters. And the number of means and variances, well, means and variances come about from continuous variables. And how many continuous variables do we have? Well, we have x2, x3, and y1. So we have 3 such variables. So 3 means, 3 variances, adding to 6. And then I claim that we have 10 thresholds. So what's that? Well, we have 6 binary ones. That is 6 thresholds. A 7th threshold for the binary x1. And an 8th threshold for the binary y2. And then for y3, we have 2 more thresholds because it is a 3-category ordinal variable. So that gives you a total of 10 thresholds. So you can see that when you have many variables, the number of H1 parameters can get quite large and sometimes prohibitive. So what's happening here is that we estimate this H1 model using Bayesian analysis. So in Bayesian analysis, the unknowns are not only the number of parameters, 82 in this case, but also the missing data. So we calculate missing data values in the Bayesian iterations. So as a side product of that step, that Bayesian step, we get not only the H1 parameters, but all of the missing data as well. So once the model has the Bayesian analysis has converged, we draw 100 more draws in the MCMC, Markov chain Monte Carlo sequence, to get the imputed values for the missing data in the model. And then that is what we use to produce the imputed values for x1 and x2. We could also request the missing data for y1 and y2 if we wanted, but that's not what we're doing here. The save data information says that we're saving x's and y's and n as expected into a data file called imp_star.dat, which on slide 66 is expressed this way. So we're talking about the last step of 3-step after imputation. The file is then implist. So that's a file that lists all of the 100 data sets and points to them. And now the variable type here, or the data type rather, is type equals imputation. So type equals imputation data. And the variables are the ones we saved, and we use these variables in the analysis in the model over on the right, and the n is a nominal variable, and the y1 and y2 are categorical. And missing is, like before, 3 classes, starts equals 0 because it is the last step. And note then that we have not designated x1 as categorical, and that's for the following reason. Over here on the right in the model, We have C on x1 to x3 and y1 through y3 on x1 to x3. So the x's are all covariates, exogenous, independent, and therefore, since their x variables are independent, you don't have to specify the variable type. It's x1 is just a dummy variable. So that's one thing to note. And the other thing to note is that there is no x part, no x1, x3 with x1, x3, because we don't have to bring the x's into model because the x's no longer have missing data because we imputed for it. Otherwise, the model is the same as before for 3-step, the fixed nominal variables at the fixed loaded values. Let's take a look at the outline on slide 67. We're going to talk about a combined approach for doing imputation and the final analysis step together, where we can do all three methods, 3-step, BCH, and 2-step. Just to remind you, we are now within the manual multi-step area, and we're looking at distal outcomes together with covariates that have missing data. And we looked at three alternatives first, ML and integration, Bayes, and multiple imputation. And again, now we're going to combine this and do imputation together with all three methods. Slide 68 then is a brief discussion of the two stages. First stage, which is really first step, it's a measurement model analysis once again. It's just with the slight change that we save data that can be used by all three methods later on in the final step. And instead of steps, we talk about stages here. Stage B is then the combined imputation and final analysis. So the reason for doing that is that one key advantage is gained by keeping the number of data sets to a minimum, as you will see. Now, you can also imagine when you have imputation needs that you want to do the imputation in a separate step. Here you do it together with the final analysis. And if the imputation takes a long time and you want to do many final analyses, maybe you want to do the imputation and save the data so you can come back to the imputed data, don't have to redo that. Well, but you can do that saving of the imputations also within this stage B using save data and then set data type imputation. So I'll show that in the input. Now, multiple imputation can be skipped, of course, if you don't have very much missing data on the covariates, or replaced by integration or Bayes. But we're assuming here that you have a real need for doing imputation. So here's an overall picture of the analysis stages for this combined approach. Stage A, the first step, is the measurement model analysis, and stage B is the final analysis with multiple imputation and full model analysis. So the input specifications then are that we have the use variables 1 through 6 for the latent class indicators. And that's what we use in a measurement model analysis. And those variables are then saved for a last stage analysis. And we have the auxiliary option for the final stage, which has the covariates and the distal outcomes on it. And then we request CPROBs for which we use for 3-step. So we have the three class probabilities for the three classes, and the most likely class, the nominal variable that we abbreviate to N. And we ask for BCH weights for the BCH approach. So we get 3 weights here, 1 for each class. And we also ask for S values, saving the measurement model parameter estimates for the 2-step analysis in the final analysis. So in the stage B, then, you have the 3 approaches following the data imputation. In 3-step, we have use variables N x1, x3, y1, y3, and use the logits from stage A, which you add manually then for the last stage. For BCH, you have a slightly different use variable list, only the x's and the y's, and the extra information that BCH needs is put into the training option, weight 1 through weight 3, BCH in parentheses. For two-step, the use variable list is still different. You have to mention the latent class indicator variables in addition to the x's and y's, because they are given s values from stage A, manually added again. So for three-step and two-step, as usual, we have to manually add things for the last step. BCH is a little simpler. You don't have to add anything manually. All you have to do is type this. So BCH can be preferable from that point of view, although it has its shortcomings as well, as we will see. So there are pros and cons for all three methods. Turning to slide 70 then, let's take a look at the stage A, the measurement model. So we work with the original data set, distal.dat, and here are the names. And we have use variable list, only the indicators. And the auxiliary variables are the x's and the y's. And what we do differently here is to save data. We save CPROBs and BCH weights, both of them, plus S values that are requested within the output command. As an aside, in this run, we need to reorder the classes because they come out in different order relative to other runs that we do to be able to compare the results easily. So we do an S values reordering of the classes. The second class in the run here should be the first, etc. So the save data information now is all of the latent class indicators, all of the x's and y's, the BCH weights, and the CPROBs, and the most likely class that's three-stage needs. Slide 72, then you have stage B, the final step, and let's take three-step first. So the data file is the stage A data that we created in the previous stage. And this is the names list that we just looked at. Use variable list, as we noted earlier, is x's and y's with n added to it, the nominal n. And the categorical variables are y2 and y3. We don't refer to the binary x1 because it is not a dependent variable in the model later on here. So the use variable list here refers to the variables in the model command, as usual. Data imputation is, as we described it earlier, the names list shows all the variables that give information, that carry information used for the imputation, and imputation is only for x1 and x2, where x1 is binary. And we have request 100 data sets, and in this case thinning is only 10 as opposed to 100 before. It's probably sufficient. And here you can say that you want to save these imputed data if you want to, if you think you're going to do a lot of analysis, and if the imputation step took a long time, then it may be useful to save it. Otherwise, just do the imputation over and over again for every analysis variation that you want. So the analysis is a mixture model. Estimator MLR starts equals 0, as usual for the last step, and then C on X, Y on X, and no X part, because the X's no longer have missing data. And just like before for three-step, we fix the logits from the first stage to the same values as we've seen before. Slide 73, we do the same thing for the BCH method. So the data is the same. The use variable list is different. It's only the x's and the y's here. Categorical is the same as before. And now we add training where we refer to the weights of the BCH. They're sitting up here in the names list. And the imputation is exactly the same as for 3-step. And the analysis is the same as well. Nothing really new there. So it's easy to switch from 3-step to BCH and also to 2-step. So in 2-step, we have, again, stage A data. The names list is the same. The use variable list changes. You have to remember to include the latent class indicators here, and they are declared as categorical. And the imputation is exactly the same as for 3-step and BCH. And on the next slide, we see the rest of the model. It's a mixture model, starts equals 0. And here's a little note. You can add B iterations, increase the default for the imputation step if you want to. You do it here in the analysis. You could have done that also for BCH and 3-step. And the model is the same, C on X, Y on X, and no X part. And now what's different for 2-step is that we have these fixed thresholds, these measurement parameters that are key for 2-step analysis. The outline on slide 76 shows that we are now ready to compare results using the manual approaches. Let's remind ourselves about the model that we're considering. We have the latent class indicators, the distal outcomes, and the covariates. And one key question is, where in the Mplus output do we find the various results? And I like to summarize the parts of the results by using these causal arrows, the X to Y influence, the C to Y influence, and the X to C influence. So X to Y is what we're showing here on the right side of the figure. So that's in Mplus language Y on X, Y regressed on X. And with continuous Y, that's regular linear regression slopes that we find in the regular model results section. For categorical Y, we have added a special section, logistic regression odds ratio results. So that's in addition to the logits that we give in the regular model results section. For C influencing Y, that is C influencing Y up here, those arrows, what we're looking at are intercepts for Y or thresholds for Y. With continuous Y, these are the linear regression intercepts, that is the brackets for Y, which are shown in the regular model results section. With categorical Y, we're more interested in odds ratios in addition to the thresholds that are given in the regular model results section. So we have a special section on odds ratios for that. Finally then, X influencing C, so this part of the model, that's a C on X regression, which is a multinomial logistic regression. And in addition to the regular model results logits, we also give odds ratios for that. We're going to take an example showing in the output parts using BCH. On slide 78. So here we have X to Y results for final step of BCH. So at the top here, the top table, we're talking about Y1, which is continuous, and at the bottom, we're talking about Y2, which is binary. So what we have then is a regular regression, linear regression Y1 on the X's with their standard errors and the ratio of the two, and we see that all three of them, all three X's, have a significant influence on Y1. At the bottom of the table, we have Y2, the binary one, and here we're looking at the logistic regression odds ratio results, where we would then be interested in the odds ratios and their 95% confidence intervals, and whether or not the confidence interval covers 1. So here it doesn't, so X1 has a significant influence on Y2, and so does x2, and x3. Now, here, in this case, in this model, these regression slopes or odds ratios are the same for all classes because we have a class invariant y on x regression specified in the model. If you look at the C to Y results, continuous Y, we have intercepts. So the effect of C on Y is captured by the intercept varying across classes, class 1, class 2, class 3. We don't have a regression Y on X language, but instead you see the effect of C on Y in these intercepts in the regular results section, model results section. C to Y results for categorical Y. We're going to focus on the bottom two sections of this table. We have Y2 and Y3, Y2 being binary, Y3 being polynomous, ordinal. So we compare class 1 to class 3, seeing if there's a significant effect on Y2 in terms of the odds ratios. And the odds ratio has confidence interval that does not cover 1, so latent class 1 compared to latent class 3 does indeed have a significant effect on Y2. For Y3, however, there's not a significant effect because the intervals cover 1, and we saw that earlier as well. So this is class 1 compared to class 3, class 2 compared to class 3. We have insignificance for Y2 as well as for Y3. So it's a class 1 that is the one that has most of the effect here on the distal outcomes. Going to slide 81 then. We have a regular C on X regression, C#1 on the 3-axis and C#2 on the 3-axis. C#3 slopes are fixed for identification purposes as usual. So here we find that X1 has a significant influence on the first class relative to the last. So does X2 and X3. But for class 2 versus class 3, there's not an effect by X1, but there's a significant effect by X2 and not a significant effect by X3. I think I said that right. All right. That's where we find the results. So now a reminder here on slide 82 about which approaches we have available with missing data on covariates. We have ML and numerical integration. We have Bayes. We have multiple imputation. And we have the combined imputation and final analysis possibility, which is available for all three methods, just like multiple imputation is. Slide 83. This is a bit of a technical think piece slide. Not incredibly important, but it's a good way of thinking about both analyses and simulations. So now, when we're going to compare the multi-step results across methods, what's the best basis for comparison? Well, the full model is what we want to consider with indicators, covariates, and distal outcomes. And we can get results for the full model in a couple of different ways. First of all, we have a correct full model that generated the distal.dat data set. I mean, that's typically unknown in real data, of course. Here we use the Monte Carlo simulation. The data generating model population command specifies the probability of missing data on x1 and x2 as functions of the non-missing x3 variable. We show that in appendix slide 135, how we generated the data. So here we know the missing data mechanism. When x3 increases, the missingness on x1 and x2 increases. I think it's increasing, could be decreasing, but it's a function of x3. Now, the model, the analyzer generated the data, correctly specifies x1, x2, and x3, shown on slide 137. And those results agree. So that's treating the generated data as real data. So we can compare to that. Another comparison is the one-step analysis of the data generated by the model that we know is correct, but bringing x1, x2, and x3 into the model using with instead of the on that we have here, because the missing data mechanisms is unknown. So this is most close to the situation with real data. And the one-step analysis is motivated here because the true model follows the model used in the one-step. The one-step analysis does not have that distorting effect of distal outcomes or covariates due to how the data were generated. So we say x1, x3 with x1, x3 as we talked about earlier, and that's an approximation of the correct model, but one that more closely represents real data analysis. But a key comparison is with the class probabilities of the measurement model. Nevertheless, we're going to take a look at several model parameter estimates. One step with integration is done this way, and it's very familiar to what we've seen before, so I'm not going to talk about it much. We use algorithm equals integration Monte Carlo, and we have x1, x3 with x1, x3, getting two-dimensional integration. On slide 85, we start the comparison of LCA class probabilities across different approaches. So on this first slide, 85, we're going to take a look at maximum likelihood estimation using integration. The first model we consider is the correct full model, that is the model that generated the data shown on slide 137, where we know the relationship between the x's. And here are the class probabilities. Turning to the one-step approach, we act as we would when we don't know the missing data mechanism, and we simply covary the x's with each other like this. And we get these class probabilities, and we see that there is a slight difference here and here, but not very much. So we can consider the one-step model to be the correct model here. Usually in simulations in the literature, the focus is on models where one step gives bias relative to the multi-step approaches. But here, while one step is actually a correct approach to which we can compare other approaches. So let's turn to a multi-step approach. First one is three-step, and we consider the measurement model here first. 0.263, close to that. 0.291, well, there's a bigger difference. 0.446 is also a bigger difference. So this model, one-step model, a full model, is correct, but the measurement model is only a part of that, and it would only be expected to give the same results when you have a very large sample where part of the model gets the same estimates as the full model if the model is fully correct, or if you had many different replications in a Monte Carlo study. So these differences are what you would expect in a single replication analysis, so to speak. So that explains that. But we're going to focus on the agreement between the first step and the last step. And you see here that we get fairly close, but not exactly spot on. But it's close enough, I would say. VCH cannot do integration, so let's see what two-step comes up with. First step measurement model, of course, that's the same values as for three-step, the same measurement model. And now the differences are also quite small and I would say ignorable. Slide 86 then, let's take a look at Bayes, using Bayes in the last step. And the first step probabilities are the same as usual. And the last step then is a little bit, once again, a little bit different, but not far off. Two-step, similar behavior, similar but not the same. The 0.283 here for two-step disagrees a little bit more with 0.291 and then the ML that we used on the previous slide. So one could say that Bayes does a little bit worse than ML in matching here for the second class. But it's hard to say from a single replication, that single data set. You need simulation studies to decide on that. Turning then to the multiple imputation using the combined approach. You have three-step here, same degree of discrepancy, not a lot, but a bit. And VCH, however, manages to nail it right on target here. So it does very well in this multiple imputation combined approach. Two-step, a little bit different once again. So that's the latent class probabilities, how they compare from the first to the last step. Now, if you look at other model parameters, and we have here the one step with integration. You have x to y here. That's a regression of y on x. C to y, changes in intercepts or odds ratios. And x to c. What we're going to take a look at is not the numbers per se, but significance. So we have asterisk where there is significant results. Now, on slide 88, we have the ML combined approach. And if you compare with the previous slide, there is non-significance here for this value, whereas we had significant for one step. And we actually have significance for other approaches. So here's BCH. BCH gets that significant. And so does two-step. Now, slide 89, going back to that, we have a non-significant value here for BCH, whereas it is significant for three-step and significant for two-step, and it was significant also for one-step. But by and large, one could say on slide 91 that the results differ somewhat across multi-step approaches, even for a model that is what I call largely correct. You know, we don't specify the missing data mechanism exactly correctly when we just correlate the y's, correlate the x's rather, bring them into the model, or do the multiple imputation. We don't take into account the correct missing data mechanism because we typically don't know what it is. But the differences are small, ignorable I would say, and do not, by and large, do not change significance of the estimates. And you have to keep in mind that these results are based on Monte Carlo generated data from a single replication. A literature summary of Monte Carlo studies with many replications, which is what you need, is to date, the summary to date is given in the statistical methodology section, showing that the choice of best multi-step approach depends on the circumstances, some of which are unknown and unknowable also. And I think that for any given data set, it may be warranted to study results from all the approaches and see which results do and do not hold up. With a combined approach, for instance, it's not hard to do all three analyses, all three multi-step approaches, and then see which results hold up and which don't. Turning to the outline on slide 92, we're now going to take a look at the real data example. This uses antisocial behavior measures that I have been analyzing earlier. The data is called the ASB data, and it consists of 17 antisocial behavior items that were part of the NLS, National Survey of Youth, for people between ages 16 to 23. And the items assess the frequency of various behaviors during the past year, dichotomized here as 0 versus more than 0 times. So it's a good size sample, over 7,000 respondents, and it has complete data on the antisocial behavior items and the background variables. So unfortunately, the data is not quite realistic in the sense that we have already eliminated some people with missing data, probably particularly on the background variables. So in this case, we have no missing data on X. The ASB analysis that I've done in the past is four-factor analysis using a mimic model in my handbook chapter for the Cambridge University Press, coming out soon, but also in latent class analysis from Mplus short course topic 5, where I go through 4-class and 5-class LCA of these 17 items. The 5 classes are high on all items, high on property offense items, drug items, person offense, normative, that is low on all items except for pot. And these data are available here for you to practice with. On slide 94, I show results in probability scale that you get from the Mplus output. And you also have the class probabilities. So you have the 17 items here as rows and the 5 classes as columns. So for those in the high class, they have a high probability of saying yes to having engaged in these activities. So they're high on everything, on all the items. About 2% of the sample are high on all items. The second class is a property tax with 12%. Third class is a drug class with 17%. Person offense is 26%, and the low class 43%. We talked about the high class. For the property class, you have a high probability for engaging in property. I think it's property theft and shoplifting, stealing less than $50, conning someone, auto, building, goods. So the way I bold it is for the property class here and the property item, I bold 0.65 here because I don't have any, it discriminates well against the other 3 classes here. I don't bold it for fighting because we have a fairly high probability over here for person offense, so it doesn't discriminate, that item doesn't discriminate that well between the property class and the person class. Shoplifting, however, does discriminate well, and less than 50. For some reason greater than 50 is not that important or maybe it's just rare. Threat is high, but it's also high for person. And same for pot, it's high for the drug class, so I don't bold those values, etc. down. So we have several items then that discriminate well for the property class, but we only have 2 for the drug class, so that could be, the measurements could be beefed up there to, if you want to capture a drug class well, we should add items. For person class, we have 2 that are reasonable, but they don't discriminate well against the property class. We have 0.50 here, we have 0.65 there, 0.65 here, we have 0.76 here. So that's a weakly measured class. The low class is probably well defined. You know, it's low on every item except pot here, 0.20. So it's a fairly weak solution, but you know, one that is probably commonly encountered, at least in the first round analysis of a measurement instrument like this. Slide 95, I do an analysis of these 17 indicators in a one-step analysis. So I bring in the 9 covariates that we're going to consider and the 2 distal outcomes. So here's a data set, name, ASB free, and names list is like this. We have the use variable list for this one-step analysis, the 17 latent class indicators, property through gambling, property down to gambling here, and we have 9 covariates, male, black, etc. to age 94, and we have 2 distal outcomes, which we call DEP and abuse, and that has to do with alcohol dependence and alcohol abuse. The categorical items are property and gambling, and the distal outcomes are not considered categorical in this analysis, therefore treated as continuous. So we do mixture modeling, and we have a good number of random starts because 5 classes is a lot, particularly when they're not that well defined. And I use processors equal 12 here to speed up the analysis with many starts. So in the model we have the latent class variable C with 5 classes regressed on the covariates, male through age 94. And we have the distal outcomes, DEP and abuse, on that same set of covariates, male through age 94. And then we add DEP with abuse here. So that refers to a within class correlation between the 2 variables. You know, the 2 variables would correlate because they're both influenced by a latent class variable. So the latent class variable behind them is making them correlated. But here we're asking for within class correlation. I don't know to which extent that's necessary. It is true, however, that many of those who have alcohol dependence have alcohol abuse as well. It's not a perfect relationship, but they're definitely correlated. And we'll get back to that issue of using with or not for the case when you have several distal outcomes. That's all we have to say, because in the model specification, because the property through gambling thresholds and the dependence and abuse means vary across the classes by default. Now, slide 96 though. Here we have an interesting case. The one-step analysis actually fails. The input of which I just showed you. The best log likelihood cannot be replicated even at this high starts of 1200, 400. And the likely cause is that the distal outcome data confound the relatively weak 5-class solution based on the latent class indicators. So it's like the distal outcomes pull in a different direction towards a different mixture solution than what you get for the latent class indicators, those 17 items. So this makes multi-step approaches not only preferable, but necessary. Can't get a solution otherwise. And you can take any of these three then, and we're going to demonstrate BCH here for the final step. But on slide 97, you have the first step analysis illustrated. So this is the measurement model. The use variable list is then the property through gambling, those 17 items, and we comment out all the other variables, covariates and distals. But we are going to use the covariates and the distals in the second last step, so we put them on the auxiliary list to be saved. And we declare property through gambling as categorical. In this case, they're binary. And then we do save data. In line with the combined approach, we're going to prepare for analysis with either 3-step BCH or 2-step. So we save CPROBs for 3-step and BCH weights for BCH and S values for 2-step. So we have them available. Let me save them in a data set 1792, referring to the number of variables for indicators, covariates, and distals. So then the last step of BCH, we're only illustrating BCH here, uses that data set and the names of that data set, the variable list that's saved, has then the weights and the C probabilities and that most likely class nominal variable n used for 3-step. So now the use variables is this list, the distals and the x's and the weights are declared as being part of the training option using BCH. It's the last step, so we do starts equals 0, and the model is C on X, Y on X, so to speak, and within class correlation between the two distal outcomes, the two Y's. So on slide 99 then, I summarize the analyses. 1 step fails. Best log likelihood cannot be replicated. First step analysis, which is the measurement model, latent class indicators only, those 17 items. Class probabilities are like this, which is exactly what I showed you before, and it agrees with the short course results. So you have the classes that we discussed earlier. Now if you take a 3-step approach, which I didn't show you the input for, but which you can now do, I'm sure, adding the covariates and distal outcomes, the last step class probabilities are like this, which is a complete failure to match the measurement model probabilities. The probability of 0.737, for instance, does not exist among the probabilities for the measurement model. So that's a complete failure. BCH, which we illustrated, here the class probabilities are like this. So 0.019 agrees perfectly. 0.118 is close to 0.117. 172 agrees. 260 almost perfect. 431 is perfect. So that works really well here. BCH works well. What about 2-step? Well, there the class probabilities are like this. Again, a very high class probability, 0.648, which cannot be found in the measurement model, so it's a failure. And if you try starts greater than 0, which we're going to discuss in the extra topics, the further topics section, it gives a better and replicated log likelihood, but with class probabilities that also don't match well. So the only method that works out of these three is BCH, which is interesting. So, concluding then on slide 100, the superiority of the BCH approach is actually agreeing with simulation findings that I show in the Monte Carlo studies overview later on in the talk. And you can actually see the reason for that if you ask for Mplus to give you class-specific histograms of the distribution of the distal outcomes, it shows strong within-class non-normality for dependence and abuse. And that violates the assumption of within-class normality that the model is using for continuous outcomes, which then causes bias for 3-step and 2-step. And only BCH survives that problem. Now, in this case, I treated the distal outcomes as continuous outcomes, which is not optimal, clearly, because we have very strong floor effects. Many of these individuals have no signs of alcohol dependence or abuse, so they're at 0. You can ask yourself, would the comparison of methods turn out differently if you treated the variables as continuous but allowed the variances for the distals to vary across the classes? You know, like that setting that we have for distal DU 3-step in the automatic, can allow the variances for the distals to vary across the classes. Would that do better, make for a solution that was trustworthy for 3-step, for instance? And would the comparison of methods turn out differently if the distal outcomes were dichotomized and treated as binary? That may be a better alternative. Or perhaps the distal outcomes should be treated as censored, so strong floor effect, but then a continuous tail. Or should be considered as 2-part, semi-continuous, which also considers continuous variables with a strong floor effect. So those are possibilities you can explore with the data and see if you can find solutions using the other 2 methods than the other ones than BCH. Finally, then, on slide 101, another caveat in the analysis is this. ASB is a general population survey, so you can expect considerable heterogeneity among the individuals in the sample. Not everyone reacts the same way to these items. So measurement non-invariance differential item function is likely for some latent class indicators as a function of some covariates. So you have a need for including direct effects from covariates to indicators. So certain groups of individuals, for instance, react differently to these different items. And that is the case. There's a lot of examples of that in this data set. Ignoring direct effects cause bias, especially for C on X parameters. So we have a Webtalk 9 which discusses how you search for and take into account and evaluate direct effects. And that's called Using Mplus to Investigate Direct Effects in Latent Class Analysis, Webtalk 9, as I said. The outline on slide 102 shows that it's time for further topics, so extra topics that are not the central ones to this talk, but still important ones. And we're going to start with the class varying regression. And I'm referring to the regression of distal outcomes on the covariates. So slide 103 shows 2 pictures. Top left, you have the indicators, in this case 3 latent class indicators, and a distal outcome and a covariate. So a simplified version of the models we looked at. And the model on the left here has 2 main effects. This is the effect of X on Y, which is captured by the Y on X regression coefficient. And we have the effect of C on Y, which is this arrow, which is captured by class varying Y intercepts for continuous outcomes and thresholds for categorical. Now, in contrast, the model on the right is more complex. It has this broken arrow added to it. So that designates an interaction. Broken arrow from C to the arrow from X to Y indicates a class varying coefficient in the regression of Y on X. So class varying coefficient here, varying across these classes. That's what that picture is meant to convey. So let's take a look at that case a little bit more. Class varying regression, varying as a function of the C variable. It implies an interaction between X and C in their influence on Y. So an interaction between these two variables in their influence on Y. And with an interaction, the influence of C on Y, this arrow, is no longer a main effect that can be represented by class varying Y intercepts or thresholds. And you can think back at analysis of covariance, where you have a post-test and a pre-test, and we usually assume that the slope of the post-test regressed on the pre-test is invariant across the treatment categories, which are represented by C here in this case. Now, I'll say a little bit more about this interaction case in the statistical methodology section, but let's take a look at what it means in practice. Slide 105 shows the class invariant and class varying Y on X cases in the situation of having three classes. So excerpts from the model statement. On the left we have the class invariant case, which we have seen for the application so far. Y on X, only one parameter estimated in this case. On the right we have the class varying case, where in addition to Y on X in the overall, we also specify Y on X in each of the three classes. Now the class varying regression case may be tempting because it's a fuller model, but it can cause non-convergence unless you have a large sample and the class sizes are not small. So large samples and large class sizes. In that case, it's possible to do this. And the question is it needed? Do we really need to let those slopes be class varying? So the question is, how do you test whether the class varying regression is needed? So 106 shows how you can test this statistically using an omnibus test, an overall test, and a pairwise test for these three classes. So what you do is you specify these class varying slopes and you add parameter labels, parameter 1, 2, and 3 for the three slopes. And then you use the model test command and the model constraint command. The model test command then handles the omnibus test, checking if there is any difference overall between the three slopes. And you do that by comparing 0 to the difference between P2 and P1 and between P3 and P1. That's all you need, not a third line, but only those two. So if you find a significant difference, you would like to know where it occurs between which of the three slopes. So you do a pairwise test introducing the new variables, the new parameters, diff 21, 31, 32, where you compare 2 to 1, 3 to 1, and 3 to 2. So then you get an estimate of those diffs and get their standard errors and can see if you have a significant difference or not for each one of them. In addition to that, you can use BIC, the Bayesian information criterion that you get with maximum likelihood estimation. So you can compare the class invariant and the class varying models. And we used that for the ASB example, where the class invariant case had 71 parameters and a BIC of 60,142. And then I managed to get it to converge also for the class varying Y on X case, which more than doubles the number of parameters but gets a worse BIC. The higher BIC is worse, so that the class invariant model wins. So even though we added many more parameters and therefore increase or improve the log likelihood. We paid a price for the extra parameters. We didn't improve the likelihood enough to offset the penalty for many parameters that BIC adds. So BIC wants a parsimonious model. So in this case, one would then lean towards using a class invariant model, which is more parsimonious. So that gives an additional piece of information to the statistical testing that you do up there. Continuing on slide 107, in the further topics area, we're going to take a look at some considerations relevant to the last step of the multi-step approach. So first, let's consider this issue of starts equals 0 for the last step. And that is used because the latent classes are really determined in the first step in the measurement model. Starts equals 0 in the last step is used because the last step does not really involve a mixture analysis anymore that would need random starting values to find the optimal maximum of the log likelihood. We've already decided on the mixture model. But starts greater than 0 may lead to a better log likelihood than starts equals 0. And that can mean then that either the multi-step method fails or that it actually needs starts greater than 0. So it fails when the solution gives class probabilities in worse agreement with those of the first step. And that could be due to the auxiliary distal outcome model, the extra variables in the full model, being misspecified, perhaps because it needs its own latent class variable. Now, some cases multi-step modeling may need start equals 0, but that's more seldom the case. It could be that the solution gives a better class probability agreement with the first step than starts equals 0, because the automatic starting values of starts equals 0 are not good enough for the complexity of the auxiliary model. So those are some of the more advanced considerations with starts. And on slide 109, we're looking at the issue of within-class correlation and missing data for the distal outcomes. So the distal outcomes correlate, if you have several of them, due to being influenced by the latent class variable. So when you have an underlying variable, variables tend to correlate. And the addition of within-class correlation using with, as we used with the ASB dataset, that's not available for maximum likelihood, but can be modeled using Bayes. Adding this within-class correlation for distal outcomes may improve the estimation with respect to missing data handling of the FIML kind, full information, maximum likelihood, using all available information, although in this case the Bayesian counterpart to that. And that's because with using the with statement, you can borrow information from one distal outcome to the other more directly. Now you may obtain significant correlations within class correlations, but they may be, and this is a warning, it may be due to omitted covariates influencing the two or more distal outcomes. So omitted covariate causes the within class correlation. So in that case, it may lead to worse class probability agreement with the first step because it's a misspecified model. You should really bring in the covariates. Now, an alternative to using within class correlations to improve missing data handling is to use multiple imputation for the distal outcomes. We talked about it for the X's, for the covariates, but can also be used for the distal outcomes. And in that case, it would be less reason to use within class with. All right, let's turn to the third and last further topic, for which is CPROBABILITIES, class probabilities with multiple imputation. Turning to slide 111, we're going to take a look at C probabilities, that is, class probabilities. So the focus here is on an individual's estimated probability for being in each latent class. So that gives information about how well the measurement instrument captures the individual's class membership. So let's go back to the example of 6 individuals, I equals 1 through 6, and 3 latent classes. If you take a look at individual 2, for instance, that one has a fairly high probability of being in class 3, with a relatively small probability of being in the other 2 classes. So the individual's item responses point to class 3 as the class the individual belongs to very clearly. Contrast that with individual 4, where the highest probability is 0.4, and with the other classes being fairly close to that 0.4. So not a very clear representation of the individual's class membership. So for some reason, the responses for individual 4 does not put him or her into a class very clearly. So that gives you more information about your measurement instrument for each individual. And these C probabilities are computed using 2 sources: the individual's observed value for each of the latent class indicators, or each observed variable, as well as the estimated parameters of the model, which is based on all individuals. So C probabilities can be informative. Now the question is, how do you deal with that when you use multiple imputation? And we're going to take a look at the final analysis step in the 2-step approach. So this is in a combined run, so we talk about data in stage A.dat, and the names list is this long one, and the use variables for 2-step is latent class indicators in addition to the covariates and the distal outcomes. And we declare the categorical variables that are latent class indicators and distal outcomes. In the categorical list, data imputation is like before, and nothing is changed there. We have the saving of the imputed data as a possibility. And on slide 113, we see the analysis starts equals 0, and the model C on X, Y on X, no X part because the X's have no missing data because we've done the imputation, and we have the fixed thresholds for the latent class indicators here. In addition, now we're going to ask for save data, saying save equals CPROB. And so this is not to prepare for a 3-step analysis, not that purpose, but instead for the purpose of getting individual class probabilities when you have imputed data. So slide 114 then shows how this works. C probabilities with multiple imputation. And this is a 2-step final analysis. So let's focus on one individual 1, and a case where you do 3 imputations. So imputation 1, the class probabilities here. They change a little bit across imputations. It's a little variation, random draws from this model, but they're fairly close. And in all 3 cases, the most likely class designation is class 2. And then we also can get an average for individual 1 across imputations, which is given here. So average of those. And just to orient you, the imputation results here, the first 3 rows are obtained from the save equals imputed star asterisk.dat. And the average is obtained from the save data save equals CPROB statement that we had. That gives you the average. So the average would probably be what you would want to use for that individual, although you can study the variation, the random variation here, see how well defined those, what the statistical variation is in those C probabilities. So that's from the final analysis, and you can compare that to what you get C probabilities from the measurement model, and there is no imputation here because we imputed with respect, there's no measurement error there. So in that case, for individual 1, you have these C probabilities, which can be compared to the average up here. So they're a little bit different, particularly for the second class, but not terribly so. And so that is another way of comparing class probabilities, not the model estimated one, but the one obtained by C probabilities, comparing the first step and the last step to see how well the multi-step approach works. Now, which method should we use then? Should we use 3-step BCH or 2-step? Well, slide 115 summarizes that. And we don't recommend the 3-step approach. It uses information from the measurement model in the form of the nominal most likely class variable with fixed logits, but that doesn't capture all of the information from the individual latent class indicators. So we reject that. What about BCH? Well, that does not, Mplus does not provide C probabilities for BCH because it's information from the measurement model in the form of BCH weights is not straightforward from that to get the C probabilities. And like for 3-step, not all of the information from the individual latent class indicators is captured or would be captured by the BCH weights. So we reject BCH as well. 2-step is what we recommend, and that's the analysis I showed you. Because in addition to the Y and X information in the final step, 2-step benefits from using information from the measurement model in the form of the fixed measurement parameters for the latent class indicators. So the latent class indicator, the full information from those is brought in, and therefore 2-step works well. So that's how you deal with C probabilities in the multiple imputation case. The outline on slide 116 shows that we have now come to the last section of the Webtalk, statistical methodology. And we're going to start with talking about posterior probabilities and most likely class for 3-step and BCH, where we take into account the measurement error or the classification error that is part of the MLC variable. And this really expands on the brief introduction to this topic that we provided on slides 7 and 8. So this table here looks familiar to you from that part of the talk. We show an example of 6 individuals and 3 latent classes, and the posterior probabilities are given for each individual and each latent class through the CPROB option of the save data command. And the most likely class is bolded. So for individual 1, class 1 is the most likely, and for individual 4, class 4 is the most likely, just barely. Individual 6, class 1 is the most likely. We can give a summary of this in a table with average class probabilities for most likely class as rows and class as column, where n is the MLC variable here, the nominal variable. So that is the top table of the three tables that we showed on slide 39 from the Mplus output. And that top table is just an interim step in the computation of what we really are interested in, the table of n given c instead of c given n. And n given c, that reverse probability, can be computed using Bayes' theorem, which is really just a manipulation of probabilities in a very straightforward fashion. And that table, information in that table, is used by both 3-step and BCH in capturing the measurement error or classification error in the most likely class variable. So top left here, we repeat the table that we just looked at. And now we're going to try to figure out what the interim table, what I refer to as a top table of slide 39, how it is actually computed. Probability of c given n. So let's take our time with this. So first we have n equals 1, c equals 1. So we look at which individuals are classified into class 1 when the true class is 1. So that's individual 1 and individual 6. And the probability that c equals 1, that we're in first column, is then the average of those two probabilities. So 0.5 plus 0.5 divided by 2. For the people who have n equals 1 as the most likely class, namely individual 1 and 6, what's the probability for c equals 2? Well, then you look at the c equals 2 column for those variables, 0.3 and 0.2, and take the average of that, of those two. For c equals 3 for the same people, being in the third column, as probability 0.2 for individual 1 and 0.3 for individual 6. So you put that into the average here over the two. For n equals 2, you have 3 individuals who have most likely class being 2. So you have, for those people, c equals 1 is 0.1, 0.3, 0.3. So you take the average of those 3. For c equals 2, well, then you are in the column with the most likely class. So you have 0.6, 0.4, 0.7. For c equals 3 for those same 3 people, 0.3, 0.3, 0.0. 0.3, 0.3, 0.0. And for the individuals who are most likely, have most likely class as 3, that's only one individual. So c equals 1 class membership then has probability 0.1. So you have 0.1, it's only 1. And for class 2, 0.1 again. And for class 3, it's 0.8 divided by 1. So here you have those probabilities computed for the individuals. And then you can summarize that in the table at the bottom here. So the first row is simply, so n equals 1, that's the first 3 computations. So 0.5 divided by 2 is 0.5. 0.3 plus 0.2 divided by 2 is 0.25. Same for the third one, 0.25, etc. down to the last row where you have 0.1, 0.1, 0.8, 0.1, 0.1, 0.8. So this table bottom here just summarizes what we had at top right. So turning to slide 119, let's see how we can get to the probability table for n given c, obtained via the Bayes theorem. So it looks like this: n given c equals c given n, where c given n was obtained at the bottom of the previous slide. If you multiply that by the probability of n, that variable having different values, and divide it by the probability of c having different values, you get the probability of n given c. So it may look mysterious, but it's very simple if you consider multiplying this denominator up on the left-hand side, and then it says probability of n given c times the probability of c. So that's the joint probability of n and c. And on the right-hand side, you say the same thing. C given n times probability of n is the joint probability of c and n. So you can check that you have an equivalence here between the left-hand side and the right-hand side. So we already computed c given n. So now we need to figure out what probability of n and probability of c are. Probability of n equals 1 through 3 here. Well, that's fairly easy to get. If you go back one slide, probability of n being 1 is, you have the 0.5 and 0.5 here. So you have 2 of them being 1, so 2 out of 6. And for here we have 3 out of 6, and then 1 out of 6. 3 out of 6, 1 out of 6. So that's easy to compute. Probability of C, well, that's the probabilities down here, the marginal probabilities of the classes. So those two components that we add are very simple. So now we just have to multiply it all together. The hard part was computing the first term here. So now we multiply them together, and at the bottom then you see how we piece it together. So you recognize the 2 divided by 6 and 0.30 here. And these values, 0.5, 0.25, 0.25, they come from the first row of the table on the previous slide, 0.5, 0.25, 0.25. So rows and columns are transposed. So the next column, 0.3, 23, 0.57, 0.20 is this row. And the last column, 0.10, 0.10, 0.8 is the last row down here. So that's what you get, putting the three pieces together. And if you compute these values, this is still working with the example of the 6 individuals. You can make a lot of material out of only 6 people. Then you get this table on slide 120, which we have looked at before, and corresponds to the Mplus output, the so-called middle table on slide 39 for a regular analysis. So this is probability of n given c. Why are we interested in that? Well, first of all, the output in Mplus refers to this table as classification probabilities for the most likely latent class membership column by latent class row. Why are we interested in that? Well, that table, it really represents a multinomial regression of an observed indicator n on the latent variable c. So compare that with factor analysis. So this is n is like a factor analysis indicator, and we're seeing it as a measurement error prone indicator of latent class membership. The table shows, as I say in the last bullet, and we've said before, MLC is not a perfect indicator of latent class membership. We don't have 1, 0, 0, but it can be seen as having measurement error or classification error. Now, what do we do with that then? Well, we use that in 2 ways, that table information. And for 3-step, we use it as follows, and the next slide shows how we use it for BCH. So the measurement error is translated into logits for each latent class and category of the nominal variable n. And we do that because the influence of C on n in our model is expressed by logits. So we want to translate these probabilities into loaded. Loaded for n given C divided by n last class given C. So we looked at a certain value for n, certain category for n, compared to the last category for n. So let's take an example. If you look at the table on the right here, minus 0.48, how do we get that? Well, minus 0.48 is the log of 0.26 divided by 0.42. So that's n equals 1 for the last class, n equals 1 for the last class, the last row, divided by n equals last, the third, for that same person, for that same class 3. 26 divided by 42, the log of that is minus 0.48. And we see then that the diagonal values are the highest, as we would expect. The higher they are, they come from these values, you know, on the diagonal divided by the last class. So the higher they are, the better the classification, the smaller the measurement error. So 0 is higher than the negative values here, so that's true for all three. So we make a correction for this most likely class measurement error in the last step analysis, where the nominal n variable is added to the analysis variables and given these fixed loadeds. So they come from the Pn given C table, which comes from the posterior probabilities for each individual. Now for BCH on slide 122, it's a little bit more involved, but Jerome Vermont in his 2010 paper has made a nice summary of it, or expansion of the BCH approach, because the BCH comes from the three authors of the original article from 2004, Bolk, Kroon, and Hagenars. He considers BCH for an LCA where the full model adds covariates. So the extra variables are the covariates X. So, and he considers three matrices, E, A, and D. So E is the probability of n assuming a value being in a certain class, most likely class, given the covariates for individual I. So that's a matrix with the rows, a number of people, and columns being the different categories of n, the number of classes. So that is a biased relationship with X. You know, it's most likely class regressed on X. It's not the same as C on X, the true unbiased relationship with X, which is given in matrix A. And from that then, he can also add a matrix D, probability of n equals n given C equals C, the measurement error in most likely class, which we just discussed. And the key to understanding this is that the probability of n given X, the first one, E, is equal to a product, sum over the product of C given X and n given C. So C given X, true unbiased relationship, and the measurement error relationship. And we sum over C, which is the columns of A, and it corresponds to the row of E. No, sorry, rows of D, the rows of D. And summing over that is actually then a matrix product, A times D. So that the E matrix, the biased relationship, is equal to A, the true relationship, times the measurement error matrix. So we note that E is equal to A times D, and by matrix algebra you can multiply by d inverted on both sides, and you get that A, the true relationship, is equal to the bias relationship times the inverse of the measurement error matrix. So we take the inverse of that measurement error matrix that we computed, and thereby we correct the bias relationship of E, n given x, using the inverse of D, the measurement error matrix, as weights in the regression, in the E regression, n on x. So we adjust the n on x for the unreliability in n using this measurement error matrix probability of n given c. The matrix A then contains the BCH weights that vary across individuals. We see up here that A has rows corresponding to individuals I. So those are the weights. On slide 123, the outline points to the statistical topic of missing data on a binary covariate. And we are now in the context of using maximum likelihood. And consider an example with a regression of y on two x variables, x1 and x2, where x1 is binary with missing data, and the x's are brought into the model using with. So we have y on x1, x2, and x1 with x2, like we have done in the section with missing data on covariates. By saying with, our x's are now treated as dependent variables in Mplus, so we're estimating their whole distribution, parameters of their distribution. Now x1 is not on the categorical list because ML cannot handle with involving categorical variables. There's no parameterization for it. So we are ignoring that x1 is categorical, and what happens then in the EM algorithm, expectation maximization algorithm that ML uses? Well, the expectation step for the x's does not recognize that x1 is binary, but uses a continuous variable normality assumption for it, so that expectations for continuous, not binary variables are produced. And the M step, the maximization step, then regresses y on those continuous x1 variables, except for the non-missing x1 observations, which are kept as binary. So that's an approximation that's being made. But there is missing data literature that indicates that this approximation is sufficiently good to not produce an important bias in the regression. And I give some references here from Joe Schaefer's book, and Demirtas has an article, and those references are given in our book, the Regression and Mediation Analysis book from 2016. So I talk about those matters, and I do simulation studies that support that there is not an important bias by making this approximation. But you should be aware of it. And on slide 125, you can think of an alternative, the base alternative. Chapter 10 of this 2016 regression mediation book shows that Bayes can handle this case better because it allows x1 to be put on the categorical list and allows using with. It has parameterization for that, namely a probit, underlying normality parameterization. And the simulations that I did in that book chapter show that this gives slightly better results than ignoring that x1 is binary when you have a lot of missing data, and when the missing data is not missing at random. So it's not MAR, but NMAR. But we don't have this approach available yet for mixture models in Mplus, because it requires being able to do a regression of C on x1 with missing x1. But if it proves important to include, we will add that later on. Turning then to the next statistical topic, why class-varying regression can be considered as an interaction. Slide 127 gives you a reminder of interaction thinking with linear regression as a start. So say that you have observed covariates x and c, so pretending that our latent class variable c is observed for a second. So you have y regressed on x and c and their interaction. You have an intercept as usual. So you have these b1 and b2 and b3 coefficients of primary interest. Now you can reshuffle that equation so that this term and this term get put into a summary term where you pull out x multiplying b1 is that term, x multiplying b3 times c is that term. And then you have the effect of c here. So b1 and b2 are the main effects of x and c respectively, and b3 is the interaction effect, where b1 plus b3 times c is called a moderator function. C moderates the impact of x on y. And if you evaluate that at a specific c value, we call that a simple slope. So we'll focus on the 4 parameters of the model: a, b1, b2, and b3. So how does this translate to the mixture case then? Well, repeating what we saw on the previous slide, interaction with mixtures where c is a latent class variable is what we want to consider now. So say that you have 2 classes, and say that c is scored as a 0, 1 variable, like a dummy variable. With more classes, there would be more dummy variables. So in line with equation 2, where we write it with this interaction term here, b1 is the effect of x on y for the first class, because c is 0 for the first class, so it's b1 times x. So b1 is the effect of x on y for the first class, and b1 plus b3 is the effect of x on y for the second class, where c equals 1. So the interaction is the difference in effects, that is b3. So b3 is the interaction, just like before. In the mixture notation, we write it as y equals a, an intercept that is class specific, so subscript c, and a slope on x that is class specific with subscript c again. So this model has 4 parameters, just like with linear regression. We have 2 a's and 2 b's. And in the no interaction case, and that we've looked at a lot, we have a b without the subscript, and only a varies across the classes. And the class invariant b, class invariant regression, say of distal outcomes on covariates, allows the effect of c on y to be summarized by simply by the intercepts ac. With an interaction that is bc, the effect of c can no longer be summarized by the intercepts alone. So again, I make that comparison with the analysis of covariance that I mentioned in the main part of the talk. All right, so then turning back to the outline, let's take a look at an overview of Monte Carlo studies, which is useful because you don't learn that much from a single data set. But when you generate data according to various models, you learn quite a lot. So let's take a look at slide 130. And there may be more in Monte Carlo studies that I have missed, and more that are coming all the time. But here are the key ones so far here in July of 2025. C on X, regression of C on X. And for that part of the model, Jerome Vermont, in his 2010 paper studied three-step compared to BCH, and they're approximately equal in terms of bias. Three-step has a bit less variability than BCH. Bach and Kua, in their 2018 article, show that two-step analysis can be slightly better than three-step and approximately equal to BCH in terms of bias. But two-step has less variability than BCH. So one could conclude then from those two studies that maybe one should choose two-step for C on X. But the differences are fairly small, I would say, compared to, say, three-step or BCH. We have the WebNote 21 where we looked at random intercept latent transition analysis, so more than one latent class variable, where we found that two-step did better than BCH. So maybe two-step is slightly favored in the C on X context. Let's take a look at the Y on X context on slide 131. Bach and Kua's article again claimed that two-step, three-step BCH are pretty much the same, except for when you have very low entropy. Low entropy, the multi-step methods don't work that well, generally speaking. You want to have moderate to high entropy. When you have very high entropy, you don't even need them. So there is that sweet spot, moderate entropies, where they work well. Now, two-step and three-step have slightly less variability than BCH for Y on X. But Y on X with unequal Y variances across classes, if you generate the data that way, you can see that BCH has less bias than three-step. Three-step allowing unequal variances is the best. Now, Y on X with non-normal Y within class, which is a little bit like what we had for the ASB real data example, antisocial behavior. Bach and Vermont pointed to BCH as having less bias than three-step. And Bach and Kua said that BCH is best, two-step equals three-step pretty much. And we in WebNote 21 found BCH to be the best, two-step bad, three-step very bad. So even though two-step and three-step have slightly less variability than BCH, maybe BCH is safer bet than, say, two-step when you consider Y on X. Slide 132, then we take a look at the case where you have C on X with missing data on a binary X. So that gets close to what we've been concerned with here for missing data on covariates, and my discussion about X1 being binary and ML being an approximate method. So we have DePaoli and Ja and Visser in 2025 only looked at three-step and found they created data with missing completely at random and missing at random MAR as a function of a U indicator. So they had the missingness was a function of a latent class indicator rather than what we did, where missing data on some X's was a function of another X with no missing data. So you can argue about which is most realistic in real life. It's hard to say. They found that FIML, that is maximum likelihood, approximately equal to base and approximately equal to multiple imputation. No discernible bias was found for FIML, ML, or base for C on X when X is binary with missing data. So that supports the notion that the approximation treating the binary X as continuous normal is all right. FIML uses width among the X's, ignoring that X is binary, and the way they did base was the same way They use the Mplus default to diffuse priors. If you use, that is uninformative priors, which is Mplus default. Using informative priors, of course, reduce the mean square error if you have any information about what is a reasonable prior, which you often don't have, but sometimes you do. Multiple imputation, using of X is missing on X, using X and U information, so latent class information, which is what we did. We also used distal outcome information, so that's a little bit different. Some bias with a high degree of missingness was found, with strong effect when you have strong effects of X on C. All right. Coming to the last statistical topic then, how did we generate the data, the distal.dat? So slide 134 then shows the reasoning here, where we use in Mplus we use a logistic regression specification. The dependent variable is missing or not missing for the probability of missing on x1 and x2 as a function of x3. And you see that x1 and x2 is regressed on x3. So x3 influences the missingness of x1 and x2. This is the MAR part. Whereas in bracket here you have the intercepts, and if you only had the brackets, you only had the intercept and not the next line, then you would have MCAR, missing completely at random. But we were more interested in the MAR case. At the mean of 0 for x3 here, the logit intercept of minus 1.5 translates to a probability of missing on x1 and x2 of the logit to probability transformation here, 1 divided 1 plus e to the minus logit, minus minus become plus, 0.18. So that's at the specific value of 0 for x3. One standard deviation above the mean of x3, the logit of minus 1.5 plus 0.4 translates to a probability of missing 0.25. So you have a range of missing data probabilities across the range of x3. x3 being a continuous normal variable. Now, the leading individuals with missing on one or more of the x1, x2 covariates, which is listwise deletion, creates a sample size loss of 33%, which we saw earlier. So slide 135 and 136 shows you the input for Monte Carlo generation of our LCA data, where we create and save the distal.dat. So here's a list of variable specifications: x1 binary with missing, x2 continuous missing, x3 continuous not missing, y1 continuous missing, y2 binary missing, y3 ordinal not missing. Exactly what we have used in the main part of the talk. So you generate 3 classes, and they are, the categorical variables are binary, 1 threshold, except for y3, which has 2 thresholds. It's ordinal 3 category. And you specify categorical variables here and missing, which variables are missing, and then you have a model missing command, which we just looked at, to which we add missing on y as well. So the missing on y here is missing completely at random. There's no regression on another observed variable. So it's type equals mixture, algorithm equals integration, integration equals Monte Carlo, like we talked about before. And the model population then specifies the exact values for each parameter that we have. Continuing on slide 136, where the thresholds here are the values that give the feature of classes that we have looked at. And then you have the model command, which we copy from the model population command to check that everything comes out okay. So there you have it. Now on slide 137, we analyze these data knowing the missing data mechanism. So it's a correct full model specified as the data were generated. So now we're pretending that we have real data. That's a data set we created. And we're just checking that everything comes out okay by analyzing it, not in a Monte Carlo study, but in sort of a real data study. So the specifications are the same here. Now we have to search for the solution, and the algorithmic stuff is the same. And we have then the specification x1 and x2 on x3. So that is specifying the missing data mechanism the correct way. We don't have x1 through x3 with x1 through x3 like we did before, but we have it in this fashion instead. If you and a variation on this theme is then that we ignore the missing data mechanism, we pretend that we don't know it, and that is the case actually. We don't know it in real data, and then this slide would have the with statement instead, and then this slide would represent a one-step analysis, which we showed in earlier slides. All right, and with that we have reached the reference section and the end of this Webtalk 8. Thank you for your attention.